In this video, I'll go over how to set up a destruction scene without using the Voronoi fracture and create glue constraints from scratch. Then I'll swap the geometry in this simulation that was built in the previous video to demonstrate how easy and modular this setup is. There are times you might create the fractured pieces geometry manually in a very specific way you want, and that might not use the Voronoi fracture. And in that case, you won't have the convenience of the glue constraints automatically given to you ready-made and out of the box. So in this video, I'll demonstrate how to create a very simple wall made out of stacking boxes, so you know how to build a structure from bottom up, brick by brick, and in this case box by box, without using the Voronoi fracture. Then I'll glue them together by manually creating the glue constraints and reuse the sim setup in the previous video, but swap out the wall geometry to demonstrate this modular setup and how you can reuse Dopnet setups without having to redo everything every time you change something like this. If you want a refresher on the basics of glue constraints and its fundamental core concepts, please check out my previous video on destruction glue constraints for beginners. Links in the description. So this video is a direct continuation from that one. So for the fractured wall, I want to show you different ways you can set up the constraints, simply because you might not always use this Voronoi fracture. Okay, let's take a good look at this network. You might not always use this Voronoi fracture to fracture the wall. You might want to use a different way to fracture it. It's nice that the Voronoi fracture automatically generates the constraints for us. What do we do when we use a different way to fracture the geometry? In that case, we won't have the convenience of the Voronoi fracture automatically providing the constraints for us. What do we do then? It's nice to have. It's nice and convenient. But if we don't have that convenience, say, for example, I'm going to define something else. I'm going to put a box here. I'm going to throw down a transform. And I'm going to move it over. I'm going to move it over to the right. I'm going to merge this. I'm trying to define my own pieces. I'm going to make another one. Make it move over again. Okay. Merge this in. We've got like 3 of them. Okay, I want them to be closer. Put one again. A few more. There's 4 pieces. One more. I could have used the for loop, but I don't want to complex and make this more complicated. So basically I have this box here and I moved it over by 1. And I merged it with the original box right here with this merge. And then I took that and I merged it with another box. So let me put the template here. And then I moved it over again and I merged it with that and moved it over again and merged it with that. And thus I get 5 boxes side by side. Now I'm going to move this completely over. Oops. This way. Alright. Now, it's not on the ground plane, as you can see. It's right smack in the middle. So I'm going to move it up as well. Now it's right on the ground plane. Now say I want to connect these 5 boxes together. Okay, before we head there, I'm just going to disconnect this for a second. I need to give a name to each box, which in this case, the boxes are my fractured pieces. The original Voronoi fracture node that we used to fracture the box, the wall-like box, generates the many fractured pieces automatically. It also automatically gives each piece a unique name. We have to do the same thing for the 5 boxes that I've created, which in this case is my fractured pieces. The assemble node has a handy feature for naming each individual 3D piece in a geometry by assigning a name attribute to the primitives and giving each piece an unique name. So after we create that, go to select the assemble node, primitives, and look, we have names here, nicely placed for every single piece, for every single cube. I'm gonna show you how this is working. I'm gonna put down a blast. At name equals piece 0. So this blast is isolating one piece. It's isolating, okay, if I remove the template from the assemble node, I'm telling the blast to isolate everything in the spreadsheet with the name piece 0. Only show me geometry with this piece 0 value. Only piece 0 is being displayed in the 3D viewport. If I select the assemble node here and put the render flag here, this name attribute has piece 0, piece 1, piece 2. So it's obviously naming this first cube piece 0, piece 1, piece 2, piece 3, piece 4. In the blast node, in order to test if this assemble node is naming it correctly. So this is only for debugging purposes. So I'm going to give it a black color. I also should color these two black too. So these black nodes are not being used in part of the functionality of this scene. It's only used for debugging purposes. So let's put this back here. Now I'm going to wire this. This is a nice time to point out the beauty of having these outs here, these nulls here. I don't have to remake everything here in order to switch these objects in this simulation. I don't have to redo everything like this because I already have this here. All I have to do in the fractured wall is hook this up to the fractured geo. That's all I have to do in order to replace it. And that will replace the geometry in the simulation. I'm going to put the DopImport render flag here. Notice what the 3D viewport is currently displaying after we place the render flag on the DopImport node. The DopImport node is extracting the geometry data from our destruction simulation. That's our Dopnet. And just by linking our new 5 individual boxes as our new fractured geometry to the null node named out fractured geo, it automatically updates our entire setup. So this is a very good example of how these out null nodes come in handy, and it makes the scene so modular and organized. When we need to switch things around, like switch the geometry, swap the geometry around, it's much easier than going into the Dopnet and relinking all the geometry all over again. Now I need to create constraints for these boxes. So now that we're generating our own fracture geometry from scratch without using the Voronoi fracture node, we don't have the convenience of the constraints automatically being provided for us. We need to create the constraints from scratch as well. There's a node in Houdini called Connect Adjacent Pieces. What this will do is create new geometry lines that are connected together based on the positions of our 5 individual boxes. Let's come here. So right when we add this connected adjacent pieces, this goes blank. The 3D viewport goes blank. There's nothing here. Now, select this. Piece attribute name. That's correct. Click this again. So this is what it's looking for, this name attribute. So it's called name. So we have the right attribute name here. Lower that. Max connections. Let's increase this. 2, 3, 4. Now increase the search radius. Okay, now it starts to come up. In order to illustrate what the connected adjacent pieces are doing, I'm going to rotate the boxes a little bit so you can see the lines in the 3D viewport. So basically I rotated the boxes. They're now overlapping, but I'll fix that a bit. I'll fix that a little later. I just want to show you how this connected adjacent pieces is working. I just really wish it wasn't white. Well, maybe I can color it differently. Okay, yeah, okay, that's better. So I don't need to rotate this. Red lines here. That's what it's defining as the constraint, as the wireframe that we have over here. This white wireframe here is this red here. Now what's different about this connected adjacent pieces is that it's taking the edges, the corners of the cube and finding nearby corners of the next cube and connecting them together like that. in the original Voronoi fracture here, I'm gonna take this one piece, that we were seeing over here. Oh, whoops. Let me hook this back up. This one piece here. This piece. I need to select a new piece because I had changed the point count. So these two debug nodes need to be updated. The constraint, and I'm going to template that piece. If you remember correctly, our wall constraints were connected by the centroid of each fractured piece. In the 3D viewport, you can see the dot in the middle of the piece. So that's what it was doing here. Now for our boxes, for our connected adjacent centered, it's not really doing that. It's just getting the edges. So we want the centroid. So if we select connected adjacent pieces, connection type, we can actually choose from surface points. Okay, there we go. Now see? We're getting the centroid of each cube and connecting it together to make the same wireframe. Now I'm going to lower the number of connections because I think we only need 2, a max connection of 2. The maximum number of connections a cube can have is 2, the one on the left and the one on the right. And for the 2 cubes on the edges, like these 2 cubes, they only have 1 connection point because there's no cube beside it, only on one side. So we're going to put 2 here. So I'm going to do the same thing now. I'm going to add an attribute create, and I'm going to name these wires constraint underscore name, and it will be a primitive of type string, and we're going to call it glue. Put a null out boxes constraint. Okay, so I'm missing the rest length. If we select this, the Voronoi fracture constraints this constraint output. So let's hook this back up. Let's put this null here. It came with a rest length attribute for the primitives. In my manual one, the one that I manually created here. Actually, let me just... Okay, in my boxes geometry where I manually created the constraints. So if I put it here, I don't have the rest length. I didn't even have the name until I added it here. I added the blue, sorry. I meant glue. This connected adjacent pieces, it has this length attribute. I need to check this. So now we have both. Now we have both. Constraint name and rest length. Box geometry, and I'm going to replace it with the fractured geo and take this constraints boxes and replace it with this out fractured constraints. So we completely replaced our input geometry in the simulation. Now let's jump back into the simulation and see what it looks like. Well, one thing, the thrust for the ball is way too much. I'm gonna lower this so that it's like 5. Let's just play it just to see what happens. Alright. So as you can see, it doesn't fall apart. It just gets pushed. Now I'm going to build this wall a little more. I'm going to make this these boxes a little more interesting. I'm going to move this up. So I'm going to build a wall of boxes stacking on top of each other. I'm going to turn on wireframe. I need this exactly. So I'm going to merge this together down here. So now we have 2 layers of boxes. This is second layer. I'm actually going to do another layer and then merge this. So I have 3 layers of boxes. So this will be interesting to knock down. Now let's look at the constraint, this. So that's our constraint data. Put the render flag back here. Let's go to the simulation. Go to Dopnet. So it's still loading the 5. If we look here, we only have the 5 boxes. That's because we haven't reset the timeline. Okay, there we go. Right when we reset it, it clears the cache, the simulation cache. Let's try it again. Let's just try it. So the boxes is all glued together very well right now. Let's increase this to 10 and shoot it out. There we go. Some of the boxes are still glued together. Now this is where I'm going to start introducing different kinds of glue constraints. So I'm going to type in relationship. The spring constraint relationship. This one is quite interesting. So I'm going to choose that one, drop it down, and I'm going to replace it replace the string relationship one with the glue. So I'm going to plug it in here. So we're not using glue anymore. So I'm just going to color this black. The spring constraint relationship, it too has a data name. So we can replace this with our name glue, with the glue name that we have. And let's just simply run it. That's how easy it is to replace it with these names once you have everything all organized and set up. Now you can see that this constraint is quite different. Let's give this wireframe. You can see that there's these yellow, like not only is the color different, but these constraints are not being broken. And instead they're being stretched. As the name implies, spring. It's trying to pull the cues back into place, but it's not strong enough. Let's make the boxes a lot. Go to the RBD object, which is our stacks of boxes right now. Go to the physical tab, and the density, let's lower this a lot. We can make the density a lot lower, which means that the mass will be, the boxes will be a lot less heavier. That way it'll make the spring constraint a little more interesting. Let's give it 100, and let's replay the simulation. Now the spring is too much, so let's increase this to 500. So the spring isn't, you can see that one of the boxes moved back in place. This one, let's get a good view. This one. This one right here. This second one right here. Just keep your eye on there. So the ball collides with it. It's about to fall, and it bounces back. Now this spring constraint isn't strong enough. So let's increase the spring constraint relationship and give it like 10 and reset the simulation. It's still not strong enough. Give it 100. It's still not strong enough. Essentially, you'll see that the boxes should spring back. It will bounce back into place. And give it 1,000. Okay, now the ball isn't hitting it hard enough. Initial state, let's give it like 20. The ball, I'm increasing the velocity to 20, so it's a little stronger. There it goes. Now it's springing into place. Sort of. It's still not strong enough. Let's give it 3,000. There you go. Now the stacks of boxes sort of push itself back in place. If we had glue for this would just knock the boxes all over the place. Instead, the boxes are they're springing back together. Now, if we had more boxes, this would be better. If the boxes were smaller, what we can do now, let's go back up. Let's go back up to the fractured wall. Now, this really shows the beauty of having these nulls here labeled like this, because it makes it so easy. This is the manual way of creating the constraints manually. This is the way of creating it with the Voronoi fracture. I'm going to label this creating constraints with Voronoi fracture. Now I'm going to switch the geometry back to what it was before, our original wall, by connecting this node back to the fracture geometry and this constraints back to the constraint node. That's it. That's all we have to do. I find this very convenient, very flexible, this type of setup. So that's the beauty of labeling these nodes correctly. Let's go back to the simulation and reset the timeline, and we should see our fractured geometry. There we go. Now let's go in here and let's play it. Now remember, we have the spring constraint relationship set up. So this kind of impact looks way more interesting. So the fractured pieces of the wall is trying to spring back into place, but the ball has already knocked it out of place, out of how it was. So it's a bit bent now. All the pieces are trying to go back in place, but because the pieces are jaggedy and they're not like the previous boxes stacked on top of each other, they're all jaggedy. They're kind of trying to find its place. So it's like a jigsaw puzzle springing, like a million springs trying to like fit back together, bouncing together. I thought this was pretty cool. I really like this part. Thank you for watching and sticking to the end.